Thanks for reminding me.
Thank you.
Okay. Brett, this is the first presentation, liquid-based atomic layer deposition. Thank you.
Okay. Okay. And I hadn't specified this, but I think I'm actually going to do them in the opposite order. So if you could go to slide 7 or 8 or so. One or three more or so.
All right. Production of metal oxide powder.
Yep, that's perfect. Okay. Just as,
Way to go.
okay, great. So
I had 50% chance of getting it right.
All right. Thank you. So Jim, thanks for explaining sort of the two different technologies at a high level. I want to point out here that they are related to some extent. So we have this powder producing technology, and that's what I'm going to talk about first. Those powders would predominantly be used in lithium batteries, although there are a lot of other niche sort of applications of them. And then we also, so when those metal oxide powders would go to a battery manufacturer to make a cathode, they can work like that, just as those powders, or we can coat those powders. And so we've also got a new coating technology that will be related to the batteries, but also has a lot of different applications as well. And so I'm going to get to the coating second, partially again because the powder one is actually also sort of upstream in the overall process. All right, so what is the problem here? Well, the problem is fossil fuels are cheap, but there's obviously pollution problems with those. So there's been a big drive that everybody knows about to go to electric vehicles that would run off of the grid, be powered off of the grid, and then presumably that grid would be moving towards renewables, solar, geothermal, and all those sorts of things. But the problem is lithium battery costs are still too high to really compete with fossil fuels, although they're getting very close. And really, it's to compete with the combustion engine in a vehicle. Right now, depending on who you ask, we're around $200 per kilowatt hour in terms of the power generated by these lithium batteries, or in terms of the cost per power generated by these lithium batteries. And we want to get that down to $100. And so we've got some research here that is investigating different ways to do that. All right, next slide. So that picture there on the top, or that diagram on the top, shows sort of that first synthesizing process where we're going to be making these metal oxide powders in a less expensive way than is currently done. Then those will later be coated, and I'll talk about the coating process after I talk about the metal oxide powder creation process. So the metal oxide powders, they're used to create the cathodes in lithium batteries. And what Professor Chad Zing has developed is a flame process that produces these powders at about 50% of the cost of the current powders. So it could drop the cost of cathodes by as much as 50%. And that's important because cathodes are actually the most expensive part of the lithium battery. They make up about 30% of the overall cost. All right, next slide. So what kind of markets are we talking about? Well, lithium is big and it's also growing very fast. So the lithium battery market was already at $5 billion last year, but it's expected to increase by an order of magnitude and then some by just 6 years, 5 years from now, 4 years from now. And I think that we all sort of know that, and a lot of this area of research and sort of development has been focused on the cathode because the cathode makes up such a significant part. And it's not surprising, and that market alone was $205 million in 2017, and we're going to see very, very strong growth in that market. I think most people have a pretty good idea of all the different uses for lithium batteries, but we are seeing this expand rapidly with things like the Bird and Lime scooter bikes and power tools are almost all run now off lithium batteries, and of course Tesla is making a big push to make, as well as the other car manufacturers, to use lithium batteries. So next slide. What competition exists? So the whole lithium battery market, it's an area of intense research. So there is a very complex maze of intellectual property holdings. I have read, I don't know the exact patents, but Argonne National Laboratories and 3M really own the IP on the cathode. But that's the design of the cathode. And this business that, or this intellectual property that would support a business wouldn't necessarily have to get into the production of cathodes. It really could be the production of the materials used to make the cathodes. But we wouldn't be the only company providing that, and there would be some large ones. BASF is one of those. Umicore is another. These are companies that I was not very familiar with until this lithium research that I've been doing. But those are sort of the biggest metal oxide producers in the world. Next slide, please. We have a patent pending. This one is a U.S. patent that's pending. Next slide, please. So the next stage of development is to build a pilot plant. This has all been tested at the laboratory scale, but we want to look to scale that up. The researcher does have a $2 million DOE grant, and we're towards the end of that. And the end of that is when the pilot plant gets built. The pilot plant is really funded by, or at least a lot of that pilot plant. Maybe not if we would start it out from scratch, but a significant amount of that pilot plant will be funded by this DOE grant as a subcontract. And what's needed really for further development, I think investment is one. I'll probably come back to this as well, but the faculty member is interested in starting a company. I think that the faculty member would certainly benefit from somebody with some entrepreneurial expertise, particularly in this sort of area of lithium batteries or coating technologies, and that's what I'll talk about next. I think I think this is actually one of maybe the most exciting group of technologies in my portfolio, partially because it's such a fast and growing market, and we really have both of these processes that I'm going to be talking about today, the one that I already have, really are pretty drastic changes to the current state of the art, and so they really have the potential to significantly drop the cost of these materials, which is the goal of lithium batteries right now. There's probably more focus in that, or as much focus in that as there is in increasing performance. All right, so next slide, which I guess is really the first slide. Okay. All right, thank you. All right, so now you can see from that diagram, now we're sort of at the coating process. So that's what I want to talk about today. What's the problem? Well, the problem with coatings, and maybe one of the most favored coating techniques now, is atomic layer deposition. The current state of the art in atomic layer deposition is a chemical vapor deposition. So it's a subset of chemical vapor deposition, but it can be controlled at very thin layers. The morphology can be controlled very well, as well as the thickness, and they can get a nice uniform, very thin film thickness. And so as we move towards more and more miniaturization, which is sort of always the trend, right, then there's more of an opportunity for ALD, but the cost is very high. So if the costs were a little lower, probably there would be a lot of other technologies that could be improved. And so just to talk about some of the applications, the one I'll be talking about the most, the one that the PI is the most familiar with, is coatings that would be involved with lithium batteries, and it would actually be coatings on the powders. So you'd have these metal oxide powders that would have a coating that can increase performance a little bit, increase voltage, and also help with prevent degradation of the cathode. But ALD is also used on solar cells, microelectronics, fuel cells. There's biomedical applications. There's even membrane filtration and remediation applications. So the way ALD works, and that's what that little diagram up there in the top right shows, it's a layer by layer vapor deposition. And so it's real good for very, very thin films. Our solution is as well, but it's not quite as good at sort of intermediate ranges. Well, it is good in terms of it creates a nice even layer, and you can mix different layers in that. But when you get into these thicker coatings, and when I say thicker coatings, I'm talking around just 100 nanometers or 50 nanometers, and that's where the current vapor atomic layer deposition just takes a very, very long time. So go ahead to the next slide. So what our solution is, and I'll kind of tell you again where we are in the value chain or the manufacturing process is now we've got those powders that can be used, those metal oxide powders that can be used for cathodes, and now we're going to put a coating on each of those. So we're talking about nanoscale coatings on really sort of nanoscale substrates, and that's the substrate being the metal oxide. And we'll do that to improve the performance and the stability. And so now I'll tell you very little bit about how this works. What it is instead of using a vapor, we use a liquid organic solvent to act as the carrier. And then what happens is we'll have a little bit of water that will be pushed away by the oil, since those don't mix, and it'll be pushed onto these substrates, and in this case these nanoscale substrates, which are metal oxides. And now that occurs in a very nice even formula. And now when you drop the chemical precursor and it's actually used for the coating, that coating or those precursors will go and react at the water-oil interface and form a coating. We can get a much thicker coating this way, much faster, and it has excellent control. Next slide, please. So what's the market use here? Well, I mentioned a little bit about that it's really this component miniaturization. Also on flexible, well, I say that in a second. So this atomic layer deposition is largely present in almost all the high-end products that we see these days in various a wide range of industries. So it's the cathode powder coating. You can use a NAIBA, I'm not sure how to pronounce that, on these NCA or NMCs. Those are just different lithium cathode components. It can also be used on microelectronics. For example, there's all sorts of coatings that we can use on carbon nanotubes. Zinc oxide is one of them. Now, this is the largest segment of atomic layer deposition. The microelectronics market is about 40% of where all atomic layer deposition occurs. We can also use it in solar cells. Carbon nanotubes, again, are applicable to solar cells, and we can coat those with a titanium oxide. It can be used in fuel cells, biomedical applications. And interestingly, it's very good since because of the way that these could be used on substrates of varying topologies. So you can use on large substrates or these nanoscale substrates that aren't necessarily spheres, and therefore it has a good application to these flexible electronic devices. Okay, next slide, please. There's definitely competition here. This is kind of just a cut and paste from a market study that talked about all these different companies that are in it. Obviously, there are some large ones there. The market is definitely very large already for ALD. It's over $1 billion, but it's growing fast, and depending on who you ask, either 21% growth each year. I saw another one that anticipated this to be grow by a factor of 3 just 3 years from now. So very fast growing market. The largest type of coating that ALD does are aluminum oxide coatings, and that's $330 million. Now, I think that's important to talk about because this technology will work with aluminum oxide coatings. We haven't tested everything, so we don't know exactly how vast the applications are, but it's nice to know that it would apply to the largest segment of ALD. Next slide, please. The status of the intellectual property is that we've got a pending PCT. The inventor, Chad Zing, is interested in licensing this, like I said. And so I see really two opportunities. One, partnering with Chad in the battery market, or potentially focusing the coating technology, the liquid-based coating technology, to try to work on displacing a lot of the chemical vapor deposition applications. Next slide, please. So yeah, so an SBIR would be a good opportunity to investigate the feasibility of these non-battery applications. I just said that Chad wants to start a company and pursue the applications. I think what I would be looking for more than anything is somebody that has expertise in these markets, some engineering background or some technical background. I think would be very, very helpful. But like I said, I think it really is a very exciting opportunity. So next stage. So what's needed for further development? Well, I think a few things. I think, again, investment's always one of them. Like I said, that management with expertise in materials, or any of those industries, so microelectronics, membrane filtration, remediation, any of those that I showed, I think would demonstrate a nice opportunity. I think you could do this sort of low risk too, especially this ALD displacement, this atomic layer deposition displacement, where somebody could just take a chance, write an SBIR, and if it's funded, then great, then this is a company. If it's not, then look for other opportunities. But I think this would be very promising for funding. And like I said already, everything always needs investment. Investment really to test these other applications beyond batteries. And so next slide, if there is one. And it looks like there is not one. Okay. So I haven't done this in a while. I don't know if we want to open it up for questions, or if there's a way that I'm going to get those. Yeah, okay.
All right, I'm going to unmute everybody's phone. There'll be an opportunity for questions.
So other than that, and everybody knows what translucent means. I don't think everybody knows what radiolucent means, so maybe that's the reason leaving both in there, right?
All right, your phones are unmuted, so if there's somebody speaking and has a question for Brett.
Okay, if there's any, this is Jim, if there's any follow-up that you want to contact me directly or have me connect in with Brett, I'm happy to do that. Appreciate your attendance today. Thanks again to Brett, and be sure and feel free to follow up, and we'll see if we can make some connections. Thank you.
Thanks. Bye.